we want to find the curl of the vector field f. Notice in this case, the vector field f is a two-dimensional vector field. The curl of a two-dimensional vector field and the curl of a three-dimensional vector field are different. Before we discuss the difference, though, let's review what the curl of a vector field actually tells us. The curl of a vector field measures the rotation or spinning effect. If the vector field f represents a velocity field of a fluid flow or windstorm, the curl measures the tendency of something to rotate in the fluid or wind. And if the vector field f is a 2D or two-dimensional vector field, the curl of f is a scalar function. But if the vector field f is a three-dimensional vector field, then the curl of f is another vector field. And let's discuss why there is a difference. The curl of a three-dimensional vector field is equal to the differential operator crossed with the vector field f, which would give us this 3 by 3 determinant. And now if we expand this 3 by 3 determinant, we would get this formula here for the curl of a vector field f in 3D. But now if we're concerned about the curl of a vector field in 2 dimensions, the z component would be 0, so r would be 0, and all the derivatives with respect to z would also be 0. So looking at this formula here for the curl, that means this would be 0, and this would be 0. We'd only be left with the z component, which is a difference of these two partial derivatives, which means the curl of a vector field in 2 dimensions would only be the z component of a vector field, and because the given vector field f is only in 2 dimensions, we don't want the curl of a vector field f in 2 dimensions to be equal to a vector field in 3 dimensions, and that's the reason why the curl of a vector field in 2 dimensions is equal to a scalar function, which is really just the z component of a 3-dimensional vector field. And that should make sense because remember, the curl of a vector field f in 3D points in the direction of the axis of rotation. If we have a 2-dimensional vector field, it should make sense that the axis of rotation would be a vertical axis. So let's go back to our problem, determine the curl of the 2-dimensional vector field, then we'll evaluate it at 2 points in the given vector field, and look at it graphically to determine what it tells us about the vector field at that location. So looking at our formula below, p is equal to 2y cosine x, and q is equal to 4x sine y. So the curl of vector field f is equal to the partial derivative of q with respect to x, which would be the partial derivative of 4x sine y with respect to x, minus the partial derivative of p with respect to y, which would be the partial derivative of 2y cosine x with respect to y. So the curl of the vector field f is equal to the partial derivative of 4x sine y with respect to x would be 4 sine y, minus the partial derivative of 2y cosine x with respect to y, which would be 2 cosine x. So this is all this question is asking us for. Let's go ahead and evaluate this at 2 points in the given vector field, and then look at it graphically. So let's find the curl of the vector field f at the point pi over 2 comma pi over 2, which should be equal to 4 sine pi over 2 minus 2 cosine pi over 2, which is equal to 4 times 1 minus 2 times 0, which equals 4. So at this point, the curl is positive. Let's also find the curl of the vector field f at the point 0 comma negative pi over 2, which should be equal to 4 sine negative pi over 2 minus 2 times cosine 0, which would give us negative, which is equal to 4 times negative 1 minus 2 times 1, which equals negative 6. Now let's look at these 2 points in the given vector field and discuss what this tells us about the rotation at these 2 points. The point pi over 2 comma pi over 2 will be this point here, and because the curl is positive at this location, remember 4 would be the z component of the vector pointing the direction of the axis of rotation, which in this case means it would be up because this is the xy plane. And the reason that's important is because we can determine the direction of rotation by using the right-hand rule. Meaning if we point the thumb of our right hand upward and then close our right hand, our fingers are going to point in the direction of rotation. which in this case would be in this direction here. And looking at the vector field, notice how it does appear at this point the rotation would be in this direction. And the point 0, negative pi over 2 would be this point here. And notice how the value is negative, meaning the vector pointing in the direction of the axis of rotation would be downward this time. So using the right-hand rule, if we point our right thumb down and then close our hand, your fingers would curl in this direction here, which is the same direction as the direction of rotation at this point. So for a two-dimensional vector field, if the curl is positive, the rotation is counterclockwise. If the curl is negative, the rotation is clockwise. And the absolute value of the curl would indicate how strongly or how fast the rotation would be at that location. I hope you found this helpful.